Okay, let's continue. We've been looking at some of the criticisms of punctuated equilibrium. In particular, we're looking at claims that punctuated equilibrium has been refuted by studies of the fossil record. Let's consider a couple of the more famous cases that pose difficulties for punctuated equilibrium. First, shortly after punctuated equilibrium was first proposed, Philip Gingerich analysed half a dozen Eocene mammal lineages in the Bighorn Basin of Wyoming. Gingerich focused in particular on teeth size, since teeth are very well preserved, species are easily identified from just their teeth alone, and teeth strongly correlate to overall body size. So teeth are quite a good thing to look at because they're well preserved and they give you a lot of information. He found gradual evolution for many of these mammal lineages. Here's a chart showing gradual evolution among several species of condylarth. As you can see, there's gradual trends in a couple of those lineages there. Here's another showing gradual evolution of some different condylarth species. And finally, here's an example of gradual phyletic evolution followed by gradual cladogenesis in the primate Pelycodus. So, a lot of gradual change there. Now, there are a couple of points that defenders of punctuated equilibrium have raised against these studies. First, some have suggested that the gradual transition may in fact be a matter of migration of a population displaying clinal variation. A cline is when the form changes gradually over a geographical area. For instance, as you travel further towards the poles, species often display a gradual increase in body size. This kind of clinal variation, this increase in body size in colder climates, is very common, and it's known as Bergman's rule. The reason is simply that a larger body size means reduced surface area relative to body mass, so heat is conserved better. Now, the Bighorn Basin in which Gingerich's fossils were found is a fairly small area. So the suggestion is that what looks like a gradual evolution of the morphology is actually a species that displays clinal variation migrating over the area over time. If the climate gets colder, populations might shift so as to track their preferred habitats. This would give the same pattern in the fossil record as gradual morphological evolution. Now, I find this point quite interesting because it's something of an inversion of the traditional appeal to incomplete records. When the gradualist is confronted with sudden changes, he points out that the fossil record is incomplete. Well, when the punctuationist is shown gradual change, he can say the same thing. He can say that if we had the whole geographical spread of the species, what we'd actually see is that the gradual change in fossils is caused by migration, not morphological evolution. So, I mean, what all this emphasises is that when we think about macroevolutionary patterns, it is important to bear in mind geographical distribution. Just because we see a sudden change, this doesn't entail punctuation. The species may have evolved gradually elsewhere, then migrated rapidly into the ancestral region. Conversely, just because we see fossils changing, this doesn't entail gradualism. So that's just, I guess, a bit of an epistemological problem judging the fossil record. We have two very different stories that apply just as well. The second response basically repeats the earlier point we saw by Gould. Gingerich studied just a few members of a fauna containing hundreds of genera. Later studies on the entire fauna showed that most species exhibit stasis. Gould cites a later study by Gingerich himself as showing this. Gingerich's 1989 paper, New Earliest Wasatchian Mammalian Fauna from the Eocene of Northwestern Wyoming. Apparently Gingerich himself found stasis in many of the fossils in this area. Okay. Second, gradualism in the planktonic foraminifera, or forams. Forams are small amoebas, most of which produce shells of various different kinds. Here are a few images from Google. The fossil record for forams is extremely good, really as good as it gets. Several people have argued that anagenetic gradualism dominates across the entire class of forams. So this is not just one species, it's not just one genus, this is a whole phylum, very well represented in the fossil record, and gradualism dominates. Worse, similar patterns are found for many other kinds of microscopic protists, including radiolarians and diatoms. If you want the primary sources on this, here's a list of studies cited in Donald Prothero's article, Punctuated Equilibrium at 20. I haven't read all of these studies, obviously, but Prothero cites them as showing gradualism in forams and other protists. Now, in the structure of evolutionary theory, Gould pretty much bites the bullet here. He does reiterate the point that maybe gradualism among the forams is a matter of biased sampling, but he grants that gradualism probably does prevail in these creatures. But he thinks that this isn't a serious problem for punctuated equilibrium, since forams have special biological characteristics which mean we can't extrapolate from forams to other organisms. In particular, forams are asexuals, and this means that foram species are not so well defined. So among sexually reproducing animals, the line between one species and another can be drawn very clearly, since all members of a species are reproductively isolated from members of other species. If two animals are different species, they can't breed with each other. If they're the same species, they can breed. So in animals that reproduce sexually, species have very, very well-defined borders. And that also allows us to define speciation in a clear way. Speciation occurs when a population becomes reproductively isolated, when it becomes unable to breed with the rest of the species. Now, none of this is the case for asexual species, obviously. We can't draw the borders of asexual species in such clear ways, so we shouldn't necessarily expect to see the same patterns of change here. Now, I actually think that this is quite a significant concession, simply because most organisms are asexuals. If punctuated equilibrium only applies to sexually reproducing organisms, then it doesn't apply to the vast majority of species. I mean, maybe this isn't really a big deal. There's nothing wrong with having different models of evolution for different kinds of organisms. But if we grant that punctuated equilibrium doesn't hold for asexuals, we can't claim that punctuated equilibrium is in general dominant over gradualism. We can't claim that punctuated equilibrium is the sort of primary force of evolution for the biosphere as a whole. There really are, I mean, most species are asexuals. There's actually a good article by Stephen Jay Gould himself on this, called Planet of the Bacteria, which is online, and it's a nice article about the prevalence of asexual bacterial organisms in this case, not forams, but it shows how limited punctuated equilibrium is if it only applies to sexually reproducing species. A final point that Gould raises about forams, and this is worth mentioning because it has, I think, some implications for the debate about punctuationism and gradualism more generally, is that gradual trends seen in forams may be simplifications which sort of hide an underlying punctuational pattern. He cites a study by Kuchera and Malmgren called Differences Between Evolution of Mean Form and Evolution of New Morphotypes, an example from late Cretaceous planktonic foraminifera. They studied changes in the conicity of foram shells, conicity being a measure of how conical the shells are. So a shell might be almost flat, or it might have a very steep gradient. By measuring the mean conicity, so the average conicity of shells at various times, they found a gradual trend towards greater conicity over 3.5 million years, starting 6.8 million years ago. Here's a graph. As you can see, there is actually stasis for a couple of million years here, and then we get this onset of this very gradual trend over about 3 million years. But they also found that when you consider the conicity for all the specimens, rather than simply averaging the values, there's a rather different pattern. So essentially, the whole range of variation, these are all the specimens, each black dot here is a particular specimen. So we're looking at the whole range of variation. Now the whole range of variation remains pretty much stable until 68.5 million years ago. Okay, it remains until there, and then over about 500,000 years, the range of variation very rapidly increases. It more than doubles, almost doubles. the gradual trend then develops within this expanded range of variation. The gradual trend occurs by a gradual loss of the less conical flatter shells. So the actual pattern displayed here is stasis for a couple million years, followed by rapid expansion of variation, and then a gradual loss of the lower value. Now, to be clear, Gould doesn't deny that this is an example of gradualism. There is obviously a gradual trend here. The point is simply that we can also see a punctuational pattern. It just depends on how we look at the data. So studies that have found a great deal of gradualism among forams and other asexuals may well have also found punctuational patterns had they judged the data in a more kind of complete way. So that maybe lessens this problem. Okay, let's turn to what I think has been the most serious problem for the theory. We saw in the first video that the foundation of punctuated equilibrium is Ernst Mayr's theory of speciation. The whole idea of punctuated equilibrium, at least in the original article, rested on taking this theory of speciation and scaling it to geological time. So Mayr claimed that most speciation is peripatric, so speciation generally occurs when a small population becomes geographically isolated from the rest of the species. For instance, if an island is formed and a small population of the species is trapped on the island. This process is significant because it can overcome the genetic inertia of large populations and lead to genetic revolutions. Okay, so speciation by peripheral isolation can sort of accelerate evolutionary change. I explained all of this in the first video, so if you don't remember, go and review that. The problem is that many biologists no longer think that this theory works, or at least it no longer accounts for much change in speciation. First of all, the idea that very small populations undergo genetic revolutions has been challenged. No doubt it's possible for genetic drift to produce very significant and rapid changes, but in order for this to happen, the population would need to be extremely small. If a peripheral isolate consists of 500 or 600 individuals, that's far too many for genetic drift to have notable effects. The peripheral isolate would need to be founded by more like 9 or 10 individuals. And I mean, that can happen, but it's probably quite rare. And when it does happen, 9 or 10 is probably well below the minimum viable population size for many species. So it's quite unlikely that this population would actually persist. And it gets worse. So even in the best circumstances, where only 9 or 10 individuals form a peripheral isolate, evidence suggests that this might not produce much change anyway. Many laboratory studies have tried to test Mayr's idea by passing populations of flies and other organisms through population bottlenecks. So they start with a large population and reduce it to an extremely small number. The survivors of these bottlenecks are analogous to the small number of individuals who found a peripherally isolated population in peripatric speciation. If peripheral isolation leads to major genetic changes, then population bottlenecks should do the same. In both cases, we'd expect to see the same kind of sampling error from genetic drift. The results of these studies have been pretty disappointing. Futuyma's evolution textbook cites a study by Howard Rundle. Futuyma says, Rundle passed more than 40 experimental populations of both Drosophila pseudo-obscura and Drosophila melanogaster, those are species of flies, through bottlenecks, and could not detect in any of them significant sexual isolation from the baseline population from which they were derived. Another study found only slight sexual isolation in only a small proportion of the bottlenecked populations. Second, and as a corollary to the first point, many biologists now hold that large populations are equally prone to evolutionary change. The idea that there are sort of homogenizing mechanisms or genetic inertia, these mechanisms that prevent change in large populations, is no longer accepted. In particular, populations connected to the main body of the species don't seem to change any slower than populations that are isolated. So how serious of a problem is this? Well, on the one hand, it means that the entire foundation of punctuated equilibrium is completely undermined. As you know from the first video, Mayr's peripatric speciation plays a major role in the justification of the theory. On the other hand, punctuated equilibrium was always primarily a theory about the pattern of macroevolution. It says that over macroevolutionary time, change occurs by rapid change in speciation, followed by stasis for the rest of the lifetime of the species. And we don't need to appeal to peripatric speciation or genetic inertia or anything like that to explain this kind of pattern. In later years, Gould and Eldredge have adopted different explanations. Eldredge favours habitat tracking, which I think I've mentioned in a previous video. Gould favours a model given by Douglas Futuima. These explanations aren't contradictory. Habitat tracking can explain stasis, while Futuima's model explains why speciation is associated with change. So, habitat tracking. As we noted, the basic idea of habitat tracking is that, generally speaking, environmental changes don't cause species to evolve different morphologies. Instead, species simply move with their favoured environment. If the planet cools down, species will tend to move towards the equator, keeping track of warmer environments. If it heats up, they'll move towards the poles. If sea levels fall, species that live in shallow water areas will move to different shallow water areas rather than trying to adapt to life on land, and so on. All of this is actually fairly obvious. If a species is well adapted to a particular niche, then the members of a species that track that niche as it moves are obviously going to be the most successful. So there's selective pressure for movement. Obviously, if a species is moving with its environment, then from the point of view of the species, its environment isn't changing. So stabilizing selection will preserve the form of the species, resulting in morphological stasis. In the structure of evolutionary theory, Gould favours the account, as I said, given by Douglas Futuima. Now, according to Futuima, at the level of macroevolution, there is indeed a correlation between speciation and morphological change. Morphological change occurs mostly during speciation events, but he denies that speciation is the cause of morphological change. Indeed, at the level of microevolution, any population of a species can undergo change, and change doesn't occur to any greater extent among isolated populations. So, what's going on here? Well, what makes a difference is that any change in a population will be lost unless that population achieves reproductive isolation. In other words, change is lost unless the population speciates. And the reason is simple. Since populations of a species frequently interbreed with one another, any change in a population will sooner or later be degraded by gene flow from other populations. Speciation is important not because it causes change, but because it allows changes to become permanent. So that's why, from the point of view of microevolution, change is happening at similar rates in both isolated populations and in populations connected to the rest of the species. But from the point of view of macroevolution, changes are associated with speciation. If a population achieves reproductive isolation from the rest of the species, any changes in that population will be locked up. They'll be safe from the degrading effects of gene flow, and so they'll have a chance to be expressed over geological time. If a population isn't reproductively isolated, then although the changes are happening just as quickly as in the isolated population, those changes will eventually be lost. So Futuima's model explains why we have this kind of pattern of stasis followed by change in speciation when we look at it from the macroevolutionary point of view. To be clear about the differences between this view and Mayr's, first, Mayr gives a theory of how speciation occurs. Futuima is only concerned with the effects of speciation on evolutionary change. He says nothing about the causes of speciation. Second, on Mayr's account, peripheral isolation leads to a more rapid evolution through genetic revolutions, while various homogenizing processes keep the populations connected to the rest of the species in stasis. On Futuima's account, evolution proceeds at the same rate in both peripheral isolates and in populations connected to the rest of the species. Rapid evolution can occur in any population at any time, whether it's isolated or not, but if the population isn't isolated, changes will eventually be degraded due to breeding with other populations. in isolated populations, changes can be retained. So again, cladogenesis and speciation, this doesn't cause evolutionary change, it simply retains it. Futoima's theory has an interesting consequence which is worth mentioning here. We might think that the morphology of a species tracks the environment, so that if the environment is very stable, then you can expect stasis in species morphology, and if the environment is changing, you can expect changes in the species morphology. But if Futoima's model is correct, in fact we should expect the opposite. Stasis will be most common where the environment is unstable, for two reasons. First of all, unstable environments encourage migration. As the climate is changing, resources will shift, and species will move around a lot following them, as we just pointed out with this idea of habitat tracking. Species will track their favoured habitats. So any peripheral population is not likely to stay peripheral for very long if there's lots of environmental change. If all the populations of a species are moving around, peripheral populations will soon be reintegrated with the rest of the species. The second, unstable environments tend to favour ecological generalists. During environmental upheavals, any population that specialised itself to one particular niche would go extinct very quickly. There'll be strong selection for organisms that can deal with a wide range of environments. In a stable environment, local populations can specialise, which would encourage rapid change. In an unstable environment, populations can't specialise, so you'd expect less change. It turns out there's actually some good evidence for this. Donald Prothero and Timothy Heaton did a large study on the White River chronofauna, which contains a number of fossil lineages. It's actually one of the best representations we have of mammals in the fossil record. They spent several years examining 177 mammal species and found only 3 examples of gradualism. All the rest exhibited stasis. What's particularly striking about this is that during the time these species existed, it was the mid to late Paleogene, there were very radical environmental changes taking place, including what's known as the Oligocene climate crash, one of the most rapid climatic changes seen in the Americas. And yet these lineages maintained stasis through this climate crash, through these massive upheavals in the climate. So as well as providing support for punctuated equilibrium in general, this clearly confirms one of the more surprising predictions of Futoima's model. Okay, so although the basic foundation of punctuated equilibrium was undermined, it seems most biologists no longer really accept Mayr's theory of genetic revolutions. We can come up with we can find other foundations. Habitat tracking can explain stasis. We can use Futoima's model to explain both stasis and rapid change. And of course, Futoima's model and habitat tracking work very nicely together. So I think that it is a problem. It's quite a bad problem when the foundations of your theory get undermined. But the basic pattern of punctuated equilibrium does still seem to be secure. We can find other explanations, and it's the pattern, I think, that's the more important part of the theory. Okay, the final criticism doesn't take issue with punctuated equilibrium itself, but rather with how Gould and Eldredge defended it. We saw that in developing punctuated equilibrium, Gould and Eldredge contrasted their theory with the theory they called phyletic gradualism, which is essentially the idea that over geological time, evolution proceeds at a slow and steady pace. Many people have argued that phyletic gradualism is a straw man. No serious evolutionist has ever really been a phyletic gradualist. Richard Dawkins has a long discussion of this in Chapter 9 of The Blind Watchmaker. Dawkins distinguishes various different models of evolution. So we can distinguish between what he calls constant speedism and variable speedism. According to constant speedism, evolution proceeds at a precise, steady rate. It ticks along at the same speed, much like a clock. So degree of evolutionary change is exactly proportional to time. This might be the case with molecular clocks, which we saw in the last video. Then we have variable speedism. On this view, evolutionary change can occur at different rates. We can divide variable speedism into discrete variable speedism and continuously variable speedism. According to discrete variable speedism, the speed of evolution has discrete levels. So the extreme view would say that evolution can occur at a very fast pace or it stops. So that's much like punctuated equilibrium. On punctuated equilibrium, in its sort of pure form, you have very fast change during speciation and then stasis. So Gould and Eldredge are discrete variable speedists. On continuously variable speedism, the rate of evolution might be slow or fast or totally static or anything in between. Evolution has all sorts of different speeds. I guess the extreme version of this view would say that none of these speeds are privileged above the other. Any sort of speed can occur at any time. Obviously, speedism is a spectrum. Some people are closer to discrete variable speedism, others closer to continuously variable speedism. The charge is that Gould and Eldredge, by constructing this theory of phyletic gradualism, attributed constant speedism to previous evolutionary theorists. And I think I can see the point of this charge. When Gould and Eldredge talk about phyletic gradualism, it does sometimes seem like they are talking about something like constant speedism, about this idea that evolution proceeds in a kind of steady clock-like fashion. But nobody has ever been a constant speedist. Nobody, at least nobody educated on evolutionary theory, believes that evolution proceeds at a steady, constant rate. Everybody is a variable speedist. Some, like Gould and Eldredge, are closer to discrete variable speedism, others are closer to continuously variable speedism, others are just somewhere in the middle. So Dawkins suggests that Gould and Eldredge tried to make their theory seem more radical than it really is by contrasting it with a caricature of past theories. When you look at punctuated equilibrium in terms of a sort of spectrum of different speedisms, you see that punctuated equilibrium is actually a perfectly standard idea of modern Darwinism. There's nothing particularly radical about it. Now, regarding the charge that that phyletic gradualism was a straw man, I don't really know enough about the fields in question to make a judgment. One possibility I would suggest is that maybe both parties are right. It's entirely plausible that paleontologists tended to assume phyletic gradualism, while people in fields like population genetics were aware that phyletic gradualism was false. So, in that case, both Dawkins and Gould and Eldredge were correct. Regarding the charge that punctuated equilibrium wasn't radical, that it's nothing new, perhaps most evolutionary theorists were aware that evolution occurs in sort of fits and starts. But as I hope you're aware by this point, this doesn't entail punctuated equilibrium. The essential claim of punctuated equilibrium is that rapid change occurs during speciation and then the species remains in stasis for its lifetime. So this is a much more specific idea than simply Dawkins's discrete variable speedism. Discrete variable speedism doesn't necessarily entail punctuated equilibrium. Gould and Eldredge were probably the first to develop punctuated equilibrium in any kind of detail, even if many others may have hinted at it before. Gould tells a story in The Structure of Evolutionary Theory about John Maynard Smith. Anyway, they were at some biology conference and Smith pointed out that he'd proposed a theory very much like punctuated equilibrium in a paper way back in the 1960s or whatever. He was implying, well, punctuated equilibrium isn't really anything new. It's sort of, this kind of theory has long been well known about in evolutionary biology. And somebody responded to Smith with the statement, "Yes, you had the bike, but you didn't ride it." I'm probably getting all the details there wrong, but you get the idea. People may have proposed theories like punctuated equilibrium. It's one thing to propose them, it's another to develop them in significant detail. Now, of course, this raises the question, how exactly did Gould and Eldredge develop the theory? Where did they go with it beyond simply stating it? Well, that's what we'll look at in the next video when we examine the implications of punctuated equilibrium. But that's all for now, so thank you very much for watching. I'll see you soon. Goodbye.